When I say integrate something, integrate, we are doing integration of something. What do you understand by this word? Uh, don't look for the mathematical aspects. When you just hear that I'm integrating something, what's the first thing comes into your mind?
Finding the area between like a certain point on a graph.
That's the mathematical aspect. Yeah, I understand. But what's the first thing you can feel when you just hear this word integration? What's the English meaning you can bring out of it? Let's say I said I'm just uh, integrating all the works I have. I think you have heard this word before many times, right? What do you understand when you hear this word? What do you understand uh, in English, not in uh, not from the mathematical aspects? It could be the social aspect. It could be anything.
Like putting something together.
Exactly. Yeah, combine something, right? So, for example, um, economic and political integration. So, what does it mean? It could mean uh, the combination of those policies, right? Which could be helpful for mankind, something like that. So, yeah, it's actually uh, adding something or combining something. So, in maths, we'll actually um, add smallish areas together to find the bigger area. In other words, if I can subdivide my area, whatever it could be of any shape. If I can subdivide it into uh, several parts, and then if I can find areas of each of those and then add those, then I'll get the area of my desired uh, region, desired shape, right? So algebraically, obviously, we'll be finding antiderivatives. That means it's the opposite of the derivatives. You'll soon see how it's so related to the derivatives, but graphically, it's the case. That means we are going to find areas. Okay. So the definition, obviously, we'll start with this. So a function, let's say capital F, we say the capital F is the antiderivative of the small f on a certain interval if you find the derivative of the capital F, you get the small f. So that's a definition, obviously, but uh, you will see we'll be doing it in the opposite order in most cases. Okay, we'll come back to it. Let's see one example of it. Yeah, first of all, before going to the example, first of all, we want to know this. This is the power rule. Uh, Initially, we have seen the power rule for the derivatives. This is the power rule for the integrals. Now, why does it say it's indefinite integrals? I'll explain it as well because we'll see definite integrals as well. Um, so for now, we want to know this theorem, we want to know this rule, and we're going to find some basic integrals or antiderivatives. Okay, so the formula says if you have the exponent p for x, then it will be just one more in the exponent, and that value goes in the denominator as well. So x to the p plus 1 over p plus 1. And you need to have a plus c, where c is an arbitrary constant. I'll explain it as well. Why do you think, or rather, why do you actually need it? The only setback for this rule is you can't really use it for -1. Can anyone just quickly eyeball this rule and say why we shouldn't pick -1 for p, or why we can't pick -1 for p? Just eyeball this. It's pretty straightforward.
The denominator would equal 0.
Very good. The denominator will be 0. So if we have x to the -1, we can't really use this formula, because if you use that, you will see that denominator will become 0, which you don't really want. So we'll have a different value, a different formula, different rule for -1. Okay, but other than that, if you have x to the something, that means an exponent for x, for solo x, of course, then you can definitely use this formula. Okay, now let me explain what's happening here. Let me start sharing my screen of my iPad, and I would like to have you have the slides open. Okay, I'd like to have you to see these slides as well. So here I start. Okay. All right. Okay, today is 25th. And our rule says, our theorem says, x to the, let me use n, because I think you have seen n for the derivative. So I think it would be better if I can use n. So instead of p, let me show for n, okay? So if you find the integral of it, this is what you will get. X to the n plus 1 over n plus 1. And where does this n come from? It's the exponent of n, okay? And of course, don't forget to add a plus c. Okay, now I'll explain two things. Why do we call it the indefinite integral? And then I'll explain why do we need c for these indefinite integrals, okay? So we have two types of integrals. First of all, the indefinite integrals. That means we want to find the integral in general. We are not really looking for a certain area. Okay, we're just trying to find what happens in general. Okay, that means we don't have a precise region to think about. So this is the outlook of indefinite integral. The definite integral looks pretty similar, but it will have a certain region to consider, which is this. That means you'll have a lower limit. We call it a lower limit, and we call this one an upper limit. Okay, you'll have two limits, and we'll also see how to solve this, but not now. We'll have another discussion on that, okay, later on. So let's first focus on the indefinite integrals. The next question would be, why do you need this C additional C with this integral? What does it mean? Why is that important? So if you don't add this C, it actually gives me an idea that you are getting it from a known derivative, because this is the antiderivative, right? Now, let me explain it how. Let's say if you have f of x equals to, let's say, x squared, okay? And I'll take two more, f of x equals to x squared minus 1, f of x equals to x squared plus 1, okay? I'll find the derivatives first for each of these. So can anyone help me with this? What's the derivative of the first one? F of x equals to x squared minus 1. What's the derivative of this? Remember, we are finding derivatives, not antiderivatives. We're slowly building up towards it, okay? What's the derivative of x squared minus 1?
Just 2x.
2x. Okay, right. So using the power rule, we can get 2x for it, and for negative 1, it would be 0, right? The derivative of a constant would be 0. Okay, someone else. What's the derivative of x squared?
2x.
2x again, right? Because this part is actually same for all the functions. This first term is actually same. So clearly, even for x squared plus 1, we'll have a 2x. Because for 1, the derivative will be 0, right? It's a constant. So you can see for 3 different functions, I can actually find it for thousands more. I'll explain how. So for 3 different functions, I can actually get the same derivative. Can you see that? So if I find the antiderivative of this, obviously they are the same, I expect to get this in return. When I'm doing this one, I expect to get this in return. But when I'm doing this one, I'll definitely expect I'll get this in return. And obviously when I'll do this one, I'll find the antiderivative of this one. I'll expect that, hey, I should get this one. But definitely they're the same. So how can I expect these 3 different antiderivatives for this 2x? The antiderivative of 2x, how can it give us these 3 different results? And that's why that C comes handy, okay? So when I find the antiderivative, let me show you of 2, sorry. Let's say 2x dx, right? Okay. So like the way we have done it for the derivatives, for the antiderivatives, it's the same. So we'll keep the constant outside and we'll find the derivative of the function we have, which is x. Now, what's the exponent of x here? If we don't have any exponent, that means it's x to the 1, right? That means using this power rule, this one, we can write x to the 1 plus 1, because n is 1, right? So x to the n plus 1 over n plus 1. Do you agree? I'm just copying that formula, nothing else. Okay, because my exponent n here is 1. Okay, what do I get? I get 2x squared over 2, which is x squared. So you can see, even though I had 2x for all of this, I actually got this one as the antiderivative. I didn't get the other two. But if I have this c, I should have kept space here. Anyway, if I had a c here like this, now you can see this c could be anything. I can actually find it if I am given more information. This c could be anything, and this is of the form of this. Can you see that? If c is -1, I'll get this. If c is +1, I'll get this. So if we have any function of this format, x squared plus c, where obviously c is a constant, c is any constant, okay? We always write c for these antiderivatives because we don't really know what it would be if we don't have any further information, okay? It is uh, uh, calculated if further information is given. But if nothing is given, we just keep it c. So you can clearly imagine, and now let's go back to derivatives. You can clearly imagine if you have any function of this format, x squared plus c, the derivative will always be 2x. Can you see that? Because c is a constant. The derivative of c will be always 0. And for x squared, you'll always get 2x. So whatever the value of c is, you'll get 2x. And you can create any value for c. I mean, if I can give you this, 1,000,000, it will still be 2x. I can give you this, minus half. It will still be 2x. So c could be anything. We're not really concerned about it now. But we need to add this c because, at least as of now, we don't know where does this 2x come from. It could come from anything of this format, right? It could be the solo x squared, it could be x squared plus something, it could be x squared minus something, we don't know. Since we don't know, we just add this c. And we actually do it for any function, because for any type of format, if we have a plus or minus constant, the derivative will always be 0, right? So if we find the antiderivative, we just want to make sure that, hey, since we are generalizing thing, I'm giving you an idea that the antiderivative of this might have a constant. Does it make sense? Take your time, okay? Does the reasoning make sense? When, let's say, if you go to the next step, for example, calculus 2, and if someone asks you, hey, or let's say you are doing math tutoring, okay, at the math center here at our school, and if someone asks you, hey, why do you add c with the antiderivatives, will you be able to explain now? Ask yourself first whether you are convinced with this. Any question from this one? No questions at all? Okay. Let's try one more example from this power rule, and then we'll see some more theorems. Okay, let's just do it for fun. So we have x to the -5. Okay, can you do it for me? So the formula is, I'm writing it for you. The formula is when you have x to the n, in return you get x to the n plus 1 over n plus 1 plus c. So if we do that, what's our n here? What is the exponent here?
-5.
-5. So if I write, I'm just copying this formula again. If I write x to the -5 plus 1, excuse me, over -5 plus 1, do you agree with that? Again, I'm just uh, copying this formula, nothing else. I have this formula in front of me, and I'm just copying this, nothing else. Any question from this one? No question at all? Excuse me. Okay. Let me give you just a smallish problem, and then we'll go for the next theorems. So can you do it for me? X, let's say, excuse me, 5 x to the 4th for me. Yeah. And you'll get 1 minute for it. Okay. I'll ask you from the participants list that how did you do that, and I'll ask randomly. Okay, just give it a try. It doesn't need to be right. You have this formula. Excuse me. Use this formula and find the antiderivative of this 5x to the 4th and I think you are 11 in total. Okay, so I expect 11 results from you. You can send me directly in the chat. I mean, not for everyone. You can send a direct message to me once you're done. Okay. Excuse me. Okay, I already have 3 answers. That's great. That's pretty fast. Four of those. Oh, great. Brooke, you need to simplify it. Okay, so 1, 2, 3, 4, 5, 6. I've already got 6 answers, 7 now. That's great. 8, okay. 3 more. I expect 3 more. Just give it a try, right? It's pretty straightforward. You won't get any easier than this. And your homework assignments won't be this easy either. It's just a beginning, right? Using the power rule for the antiderivatives. Anyway, I think we can solve it. Probably the other three are trying to do. I hope so. Okay, so I guess only one of you got it wrong. The rest got it right. That's a good sign. Uh, if you have got it wrong, again, it's not a problem. But I'll now show how to do it, and hopefully, obviously, I'm not going to mention your name, but just cross-check your work. Okay, where did you do the mistake? So we can keep the 5 outside, of course. It's a constant. It doesn't really give us any headaches. So we can, I'm just showing you the steps. You don't need to show this line anyway when you are trying to show your work. Excuse me. Now, if we use the power rule, we get x to the 4 plus 1. Oops, sorry. X to the 4 plus 1 over a 4 plus 1 and a plus c, right? So we have 5x to the 5 over 5 plus a c. So clearly we can cancel this. So you'll have x to the 5 plus c. Okay. Any question from this? Anyone? No question at all? Very good. Let's go to the next theorem. The next theorem says, it's on slide 6, theorem 4.17. If you're keeping an eye on that, it's saying, the first part is saying the constant multiple rule. We have already seen this one, fortunately. This is the example of constant multiple rule, which is saying that if you have a c times f of x, that means this is a smallish c, by the way. This is the small c. You need to differentiate it with the integral constant. Okay, it's the capital C. Both are constants, but obviously when you're writing it in the algebraic form, you need to differentiate this, right? Okay, so when you have a constant time of function, the derivative of this would be the constant outside the integration of the derivative. Okay, oops, sorry. I guess the last part didn't appear. So this is C, by the way, not E. My handwriting. It's getting poor and poor day by day. F of x dx. Yeah. So this is what this is trying to say is, if you have a constant, you can just keep it outside and find the antiderivative of the function without the constant. Okay, the constant won't really harm us if it's associated with that function. Okay, multiplied with that function. If it's a solo function, a solo constant, we'll have a different result. I'll show that as well. But if it's multiplied with something, if it's associated with something, okay, then you can just keep it outside and find the antiderivative of the main function other than the constant. Okay, and this is a good example of the constant multiple rule for the antiderivative. Okay, all right. And like the way we have done it for the derivatives, it's actually same for the antiderivatives as well, which is the sum rule. Sum, or the let's say what do I say? It's, I think it's called anyway. I can't remember the other way to say it, but yeah, we can definitely call the sum rule, which is if you have two functions And if you are trying to find the derivative of the sum of those, then it's actually the same if you find the derivatives of the, not the derivative by the way, antiderivative. If you find the antiderivatives of this function separately and then add those, okay, it's the same. When you have two functions, that means when you can locate that, hey, we have two different functions here and we're trying to find the antiderivative of it, we can actually find the antiderivatives of those two functions separately and then add those. It will give us the same result. And it's actually true for any number of functions. It doesn't need to be for only two functions, okay? It could be any number of functions. And it's actually true for negatives as well. Okay, that means if I had, let's say, negatives here instead of the positive sign, it would have still made it would have made sense. Okay, like this. Okay. All right. Again, we'll see one example of it. Okay, and then we'll go to the next theorem or whatever we have on offer. So let's say we have x cubed minus let's say 5x. Okay. So instead of doing it like this, we can actually, using that rule, we can subdivide it like this. And we can actually do further simplification using the constant function rule. I can actually write it like this. Okay, here I have used the sum rule. Here I am using the constant function rule. Can you see how I am using this? I know that when I have this type of format, I can use the sum rule, right? Or it's actually true for negatives as well, as I said. So I can use this and subdivide this into two portions, right? And it will give me the same result. And we'll be doing this a lot of times, that's for sure. We'll have more than one term. That means if we have a polynomial, let's say, for example, if we have a polynomial, we'll use this for finding the antiderivative of that. We'll find the antiderivative of each term of the polynomial and then add those, or if we need to subtract it from somewhere, we'll do that. So the sum rule will be really helpful. And we have seen the same for derivatives as well, right? Okay. Any question from this one? Anything that you might be struggling to understand?
Would that be the answer, or would you go ahead and like go through the steps and everything like we had on the power rule?
Oh, no. This is not the answer, definitely. You need to find,
Okay.
yeah, you need to find the antiderivative from this.
Okay, that's what I was thinking.
I'm just showing that how to use this sum rule for this type of problem precisely. Any other questions? So the question would tell you, find the antiderivative of it, right? So we haven't really found any antiderivatives as yet. So that's a good question. So when you are asked to find the antiderivative, obviously you actually need to go to the very end. But I'm just showing how to use the sum rule or the constant function, right? Okay. Let's see a bunch of formula, and that would be really, really interesting. And you'll soon see why. Uh, Let me show you. Let me show uh, this slide now. I'm sorry that I'm switching from one slide, one screen to another. Uh, Here you go. Okay. So if you remember, I did say that the antiderivatives will be really, really connected to the derivatives. Obviously, by the way we have uh, defined it, and by the way we say it, the anti-derivatives, definitely it makes sense that it's related to derivatives, but you will see in most cases it's almost the opposite of each other. So for example, look at the first one. The derivative of sine x, we know it's cosine x, right? We know that. And the antiderivative of cosine x is sine x. You can see it's actually opposite to each other for this one. It will not be the case always, although for some cases it will be uh, pretty similar, but not exactly opposite. Okay, I will see those as well, no worries. But as you can see, this is exactly the opposite, right? Okay, we know the derivative of cosine x is negative sine x. See, if you actually find the antiderivative of negative sine x, it will be positive cosine x. Can you see that? Because the antiderivative of sine x is negative cosine x. So clearly, if we have a negative in front, this guy will become positive, which is exactly opposite of this. So for the trigonometric function spatially, it's really easy to remember this formula. Um, I think if you just remember one side, it's pretty easy to remember the other side. That means if you know the derivatives, it's pretty easy to remember the antiderivatives as well. Okay, and obviously you need to know all of this. If you don't know any of this, or if you mix one with another, then obviously you'll get a wrong result, right? So there are so many formulas to remember, but these will be really, really, really helpful, and we'll be using these tons of times. Okay, let's see one slide more. Here you go. Okay. The derivative of e to the x, if you remember, was e to the x, right? And it's same for the antiderivative as well. So if you find the antiderivative of e to the x, it is going to be to the x. And obviously you'll have a plus c, right? I don't really need to mention why, but for all the indefinite integrals, you can see we have a plus c. I think we had it here as well, yeah. You need to add this because we never know what was the initial constant when we found when we had found rather the derivative. So the antiderivative should have this plus c, and it's only for the indefinite integrals. Okay, you don't need to add this when you will be doing the definite integrals. You'll soon see those as well, okay? Maybe not today, maybe tomorrow, excuse me, but you will definitely see that. Okay. Oh, I guess this is the explanation of why we need to add the C. Yeah, this is the explanation of why we add a C, a constant, with the antiderivatives. And as you can see, for this format, x cubed over 3 minus x squared, let's say this is a function, for this format, doesn't matter what your constant is, your antiderivative will always be same, right? So that's why, again, we add a plus c, so that we can actually reach this if more information is given. Okay. All right. This is the same reasoning. Okay. All right. Now we'll practice a couple of antiderivatives, and then I'll show you how to find the value of c. As I said, as I promised you, that if more information is given, this value of c can be calculated. I'll show examples of this as well. Excuse me. Okay, but let's take a break now for 5 minutes to get ourselves re-energized. Okay, and I'll see you at 10:05. All right, see you in 5 minutes. All right, let us see a couple of examples, and then we can see the solution of the antiderivatives, where we'll be finding the value of c. But before that, any question out of your head which you couldn't ask before we went for the break? Anything you want to clarify maybe? Oh, someone has left the meeting because you're 11, if I remember. Now you're 10. Anyway, no questions at all? Perfect. Let's see some examples then, and hopefully you'll have some questions when you are done. All right. So again, I'll switch from the slides to the iPad. So I want you guys to have the formula open, have these two slides in front of you, so that when I'm doing a problem, you can actually see what I'm doing, okay? Which formula I'm using. All right. Let's say we have to find the antiderivative of x cubed minus sine x plus, let's say, natural log. I shouldn't say natural log. Let's say let's say 1 over x. Let's try this. Okay, so we're trying to find the antiderivative of this function x cubed minus sine x plus 1 over x. Okay, So obviously, okay, let me ask you, what's the first thing you can do? What's the first thing that might be helpful, might help the cause? What should you do? Anyone?
The derivative of sine x is cosine x.
Obviously, the derivative of sine x is cosine x. That's right. I mean, it's not exactly cosine x, it's negative cosine x, to be honest, but I assume you have considered the negative sign in front. But my question is, what's the first thing we can do here?
Would we break them all up into sections using the sum rule?
Very good. Yeah, exactly. We just need to subdivide it, or in other words, you might say we can break it in terms of the terms. We have three different terms we have like this. Do you agree if I do that? Don't trust me. I might make a mistake. Just trust the formula you know. Trust the rule you know, okay? If I write this way, do you agree that I can actually do that? Anyone? Is there anyone who is confused how I'm doing this? Okay. Let's do one by one then, and then we can replace it in their respective places, right? Okay. So what's the antiderivative of x cubed?
It would be x to the third plus 1 over 3 plus 1.
Right. So it will be x to the 4 over 4, right? Just using the power rule. X to the 3 plus 1 over 3 plus 1. Do you agree? Take your time, okay? You don't need to understand it straight away. Just try to uh, see how I'm using the formula and which formula I'm using, okay? If you can combine these two together, it should make sense. If it doesn't, please let me know. All right, next, the derivative of sine x. And I think someone has already answered it. The antiderivative, I'd say. I've been saying the word derivative for the last month or so. I think it's already a month now. We started back in May 24th. So it's more than a month now. That's why I'm saying this derivatives over and over again. But if I say this, please uh, discard that. I'm trying to say antiderivatives right now, okay? All right, so antiderivative of sine x is negative cosine x, right? Do you agree? Okay, last but not the least, 1 over x. You have the formula in front of you. Can anyone tell me the formula? It's the natural log of x, okay? The derivative of antiderivative, of course. The antiderivative of 1 over x is natural log of x. And this is actually x to the -1. If you remember, I did mention that for -1, that means the exponent -1 will have a separate formula, right? Our power rule, where's the power rule? Here you go. Our power rule, if you remember, was true when n was not -1. Anything but -1. It could be any value, right? It could be even, it could be 0. That should be fine. We'll see examples of that as well. But it's not applicable for -1. So what's the formula for -1 then? This is the formula for -1. That means for 1 over x, or x to the -1, the antiderivative is natural log of x. And of course, don't forget to add a c. This is your answer. Take your time and see if you have any question. No questions at all? That awkward silence again. Anyway, when you start doing the homework, hopefully I'll post it tonight. I guess you'll find some questions. If you don't have any question, if you don't find any questions, even after doing the homework, that means you are doing it really, really good. But I think having questions is also very good because it clarifies the doubts, if any, right? Okay, I think we can simplify just a little bit more. I think we can do it here. Don't really need another line here. So instead of having this negative negative, let's just write this way, okay? And this should be your final answer. If you can see that there are rooms for improvement, there is some terms which you can really reduce or simplify, you should do it. Because if you see the homework platform, you will see that it's written, simplify your answer, right? So if you can simplify further, if you can see that there is chances, there is ways for simplification, but if you still don't do that, you might get penalized in the homework, okay? So don't forget to simplify. If you see the question says simplify your answer, okay? If it doesn't say simplify your answer, then I think it should be fine, but it's always better to simplify. Okay, let's just see one example where x has rather a 0 exponent, or in other words, what if we have a constant? If you remember, the derivative of a constant was 0, right? Whatever the value of the constant is. But it's not the case for the antiderivative. The antiderivative of a constant, it's a smallish c, by the way, okay? The antiderivative of a constant, of an isolated constant, is not 0. What's that? Let's try. So first of all, I would rewrite it this way. It's a constant, right? So we can keep it outside. And I think I should write this way. Okay, so we have taken this c, this constant, outside. What else we actually have here? Because we are using the constant function rule. What could be the function here then? Can you think of anything? If you don't have anything, don't you have a 1 here multiplied to it? Because C is basically C times 1, right? You can always multiply anything by 1 and it will still give you the same result. So if we keep C outside, we can imagine a 1 there. I'm just trying to show what will happen if you have a constant. You don't need to show the steps though, okay? I'm just formulating the formula. Do you agree if I write 1 here? Do you agree? Is there anyone to whom it doesn't make sense? You don't need to trust me, okay? Clarify the doubts if you have any. Do you agree if I write 1 here? Okay, looks like you don't have any objections. At least none that I can see. Okay. Now I want to rewrite it more. Let's see how. If I rewrite it as x to the 0, do you agree with this? Because anything to the power 0 will give us 1, right? 100 to the power 0, x to the power 0, any value to the power 0 will give us 1, right? So you can replace this 1 by x to the 0. Do you agree? And now obviously we can use the power rule. So it will be c times x to the 0 plus 1, 0 plus 1, plus a capital C, okay? This is the capital C, the integral constant, okay? So this will be the constant times x plus the integral constant. This could be any other constant, right? It doesn't need to be the same C. So what it means when you have a constant only, that means it will give you the constant times x as the antiderivative. Any question from this? No questions at all? Okay. I think we can practice a couple, right? And then we can wrap this up with with how to find the value of C. Let me see. Should we practice or should we just go for the next one? Okay, I think, yeah. Let me show you how to find the value of C. Then we'll practice 1 or 2. Okay. All right. So far we have seen that we are just adding this integral constant capital C all the time. But now we want to know, is there any way to find the precise value of that? That means, is there any way to know where does this 2x come from? Whether it's x squared plus 1, x squared minus 1, or a solo x squared, or anything of this format, right? We want to know the value of this constant. Where does this come from? Okay, and for that, as I said, we need additional informations. Let's try that now. Okay, so let's say we have a function 1 minus 1 over t squared we want to find the antiderivative of this, okay? And in addition to that, we have one more information given, which is f of -1 will be -2. I mean, the functional value is given, okay? And from this, we need to find the value of that integral constant c. Okay, so first of all, let's try and find the antiderivative. What should we do? Anyone? What should you do? Remember, the question I'm asking is how to find the antiderivative first. I'm trying to find the antiderivative of this function, 1 minus 1 over t squared. And for this, as I said, we're trying to find the antiderivative. What's the first thing we need to do?
You're gonna subdivide?
Again, yeah, exactly. So 1 dt minus 1 over t squared, 1 over t squared dt, right? That's the first thing we want to do. Okay, what's the antiderivative of 1? What should we do now? If we have a constant, what would be the antiderivative of it? We have seen the formula a couple of minutes back, probably 2 minutes back. Just give it a try.
If you have a constant, it's gonna end up being the constant times the function, right?
Yeah, so basically, if you have 1, that means it's x to the 0, right? So you can remember this way as well. 1 is basically x to the 0. So if you use the power rule, you don't need to memorize it. You can use the power rule and get this, which is x, right? So yeah. Oh, so we're doing it in terms of t. So you expect a t here, okay, not x. Be aware of this. When you are doing it in terms of t, you'll get t, not x, right? Any question from this antiderivative? How did I get this? Or any other questions from this part? No questions at all? Okay, let's keep doing it. What should we do with the next term? We have 1 over t squared. What's the antiderivative of 1 over t squared? Anyone? To break this awkward silence?
Would it be the natural log of t squared?
Nope. That is only possible for 1 over t. Because if you remember, the formula was for 1 over x. It's not for 1 over x squared. So we can't really use it for 1 over t squared. What should we do then?
Can you use the quotient rule?
We haven't seen any quotient rule for antiderivatives, that's for sure. But yeah, it's a good guess. I mean, as long as you're trying, even if it's wrong, that should be fine. Anyone else? I have given you a hint though in the previous example, and you have actually done this quite a lot times for the derivatives. You have seen expressions, or I would say functions like this, where you have done something to find the final result, some sorts of modifications. You've done it quite a few times. I'm telling you, just try to refresh your memory. Oh, I think I have something in the chat. T plus 1 over t. How did you get that? What's the explanation behind it? Okay, now when I'll rewrite it, you'll say, that's the case. Okay, let me rewrite it first, and then I'll take your expressions. So I'm rewriting it here, okay? So I can actually rewrite it like this way. Do you agree? If I rewrite it, do you agree with this? That's the first question.
Yes, sir.
Sorry? I think someone tried to say something. I couldn't notice. Sorry about that. I couldn't understand, to be honest. I did notice, but I didn't understand what you said. What you say? What did you say again?
I was just saying that made sense because you asked if it did.
Oh, okay, thank you. Yeah. So I can always rewrite it like this, okay? So now I can use the power rule, right? So it will be, oops, I'm using green again. It will be T. I think I should do this in the same line. So instead of writing T here, just to keep the consistency, I'll write it T to the 0. You don't need to do this though. I'm just trying to do it in the same line, nothing else. So it will be T. It would be T to the -2 plus 1 over -2 plus 1 plus a C, right? So if I further simplify it, it would be T minus T to the -1 over -1 plus C. In other words, it would be this minus and minus will give me a plus. And I can rewrite it as 1 over T plus C. Any question from this? Take your time, okay? Any question from the entire problem? We haven't found the value of C as yet. We are not yet done. So we have more works to do, but any question up to this? No questions at all? Okay. Now, from the additional information we have, we'll try to see if we can calculate this constant, this value, right? Let's do that. So our first derivative was, what we started with was, I guess 1 minus 1 over t squared. So if we find the antiderivative of it, the definition says this would be the function itself, right? So t plus 1 over t plus c is actually the function, because it was the derivative and the antiderivative will be the function, right? Okay, and the additional information we have is this, I guess, yeah. So that means we just need to plug in -1 in place of t. So -1 in place of t would mean that -1 plus 1 over a -1 plus c. And what's the value of f of -1? What's the value of that?
-2.
-2. We can replace it here. -2 equals to, that's a -1, that's a -1. So it would be -2 plus c. If we solve it for c, this -2 and -2 will cancel each other. C will be 0. Do you agree? So that means finally we have the result, which is t plus 1 over t. Because c is 0, we don't need to have anything now. If c was a certain value, let's say 1 or 2 or any other value, let's say half, we would have written it here, right? But since c is 0, we don't need to write like this. It doesn't really look good. We can avoid and keep it like this. But this is how to find the value of c. Okay, so the main idea is the antiderivative is the first thing we need to calculate. Once we are done with that, then we can just use this additional information, if it's given, of course, to find the value of c, the integral constant c. Any question from this? Any question? No questions at all? All good? Okay. Now, what if I say for the same problem, can you calculate the value of c for me for f of 1 equals to 0? Can you do it for me? Let's try this one, okay? For the same problem, by the way. So that means we have f of t equals to t plus 1 over t, okay, plus c. And using this, f of 1 equals to 0, we want to calculate the value of c. Can you do it for me? If yes, how? The first question would be how to do it. Anyone? I'm just trying to see another value of c. It means when the information is different, I'm just trying to show you that we can actually get a different value for c. A non-zero value, perhaps. What should you do? Someone from the participants group? Yeah.
You're gonna plug in 1 into the equation and solve for C like you did before.
Okay, so I'm having it 1. So let's see what happens. What's the value of f of 1?
0.
0. You can replace it here. 2 plus c. So c would be a negative 2. So our final answer would be a t plus 1 over t minus 2. That's it. You can see we can have a different value for c. It depends on the additional information we have, right? So if we know the general solution, which was this, if we know the general solution, then we can find the value of the c depending on the additional information we'll have. Okay. All right. So if you don't have any question, let me give you a problem to practice. But before that, I'd just like to tell you some more ideas, which you have already seen, by the way, which is this. If your displacement or distance is denoted by s, we know the first derivative of that in terms of t was defined as the velocity, right? And the derivative of the velocity in terms of time was defined as the acceleration, right? So now if I give you the acceleration and tell you, hey, can you find the distance for me? Can you do it? If yes, how? Just try to use your intuition. Previously, we were given s, and from that we have calculated a. Now I'm saying that, hey, I'm giving you the acceleration. Can you calculate the displacement for me, or the distance you have covered for me? And
Would you use the antiderivative to find it?
okay, so if I find the antiderivative of a, what do I expect? Is it going to be s? What should I expect from that? You're doing it right, but
Should give V.
sorry?
It should give you V.
Exactly, it should give me v, right? Because I know the derivative of v is a, so shouldn't the antiderivative give me v, right? And if I just take the antiderivative of v, I'll get s. Bingo. That's what I wanted. So this could be a really, really good thing to practice. If you open the book, you will see the acceleration will be given, and from that, you will be asked to find the velocity or even the displacement, the distance. And you just need to find the antiderivative. That's it. Okay. And you will definitely have C's here and there, right? Let's say C1, C2. So don't worry if you have this, because additional information like this will also be given. Additional information like this will be given. Okay, so for finding this will be given a value. Okay, this could be anything. oh, I shouldn't write A though, because A is for acceleration. I have already used A. So let's say M and N. So using this information, like the way we have done, you can actually calculate C1. Same goes for this one. Something will be given. Let's say R and S. Oh, I shouldn't S. Sorry. Let's say X and Y. And you can use the given information to find the value of C. The procedure is same, just use this way. Okay. Use the additional information this way. That's it. This will give you a very, very good result. Okay. Now let me give you one example, or I shouldn't say example, let me give you one problem which you can practice in pairs, okay? All right, let me see. All right, let's say, what do I start with? So, okay, let's say I have velocity v of t negative 0.98 t plus a 40 and v of no, I shouldn't write v, I should give you s of 4.1 is approximately 182. So find s for me. What would be s from this problem? Okay, so this is the information you have, and from this you need to calculate the displacement s. Okay, any question from the question? I mean, does the question make sense? Is there anyone who is confused what you need to do? Or is the question clear? Okay, so let me, any question from this? See the entire calculation. From V, we have found the antiderivative to get S. Then from S, we have used this additional information to find the value of the integral constant C. And after we have replaced it into its respective place to finally get our result S. Negative 4.9 t squared plus 40t plus 100.37. Any question from this? No questions at all?